Hi, friend. Today I'm going to walk through this problem where you're given an array of size n plus of size n plus one. They're all containing integers yeah, from 1 to n, where every integer showed up exactly once except for one integer, and then you are asked to find the duplicate integer. So for example, if the input is 1, 2, 3, 4, the size of the list will be 5, where the number 2 showed up twice and every number else showed up exactly once. So in other words, given an array, you know the size, and then you also know n, and you know that there's at least one number 1, 2, all the way up to n, and there's also another number between 1 and you're asked to find that duplicates. So immediately you start to think maybe this is not such a hard problem, because we can trivially, for example, scan from left to right and store all the numbers we have seen so far and see, is this number we have seen before? So that will be a linear search, but with also O(n) space complexity. So our solution one will be iteration plus memory or memorization. So that will be O(n) time and also O(n) space. And then another trivial solution would be, what if the input is sorted? So we can sort the input, and then we can scan from left to right, and we immediately know that, oh, if there's a duplicate number, they will be adjacent to each other, and we just need to scan from left to right and see if it's equal to the immediate next number, and if so, that's the duplicate. But the sorting will take n log n, but this time we do have a O(n) space. So it seems like it's a trade-off that we have to make between space and time. But can we do better? Can we somehow combine the best from both worlds? Can we do a O(n) time and a O(n) space? And then when you think about O(n) space, immediately what you're thinking of is, okay, we have to do some modification in place. We don't get the luxury to create a new array or a new map and store some elements that is proportional to n. All we can do is have a constant number of elements, and so we probably need to use the input array to store some of our informations. And also we cannot sort them, and then the input array is not guaranteed to be sorted. And then one solution you may start to think about is, oh, can we somehow realize the property that all the numbers are between 1 and n? In other words, we know that there's no number that is going to be larger than n. And then we also have an array of size n plus 1, and all the number are between 1 and n. So does this ring a bell about how non-comparison based sorting work? So somehow if you want to sort array, what about it just create an array of enough size, and every number k, you put it at the index k, and it say, okay, now we have one occurrence of this number at index k. So one natural way to say this is to sort of utilize a similar idea that, okay, fine, we cannot use an additional array, cannot open a new array to store the elements we have seen so far, but can we just use the input array in place and modify it to record that information? And yes, we can do so. For example, since every number is between 1 and n, and if we visit a number and we somehow want to remember it using the input array by modifying some input array in place, what if we just go to the index of that number? So if we visit a number say the number is num, then we go to the array at index num, and we modify the number by increment by adding a number n to it, where n is whereas n is the size of the input array minus 1. What does that mean? It means, okay, it means that the original input, no element is greater than n, but all of a sudden we modify some of the input to be larger than n, and we know what that means. Well, the way that can happen is the number has been visited before. And another beauty about this approach is you can easily recover the original number by look at the number. If it's larger than n and subtract n from it, then you can successfully recover the original number, and you can continue to remember this number in there using the input array. And this way, whenever you visit a number and you go to the index at that number in the array, and if the number there is already larger than n, then you immediately know that we have previously encountered the same number, and that's why we have incremented this place to be larger than n. So the algorithm then will be scan from left to right. Whenever you see a number, you go to its index and you increment n at that new place, and you move on. And then the next time, when you go and visit the new the array at the index, if it's larger than n, then you find the duplicate. So that will be the algorithm we're going to do today. Maybe it'd be easier to run an example first. Okay, imagine this is the example 1, 2, 4, 2, 3. And then when we visit number 1, the first number, or what we're going to do is we're going to go to index 1, which is here, and we're going to increment n to it. So in this case, n is 4. So 2 plus 4 is 6. Okay, now we'll move on and we'll go to the second number. We see, oh, it's larger than n. So somebody else has modified the number and we want to recover the original value. And we can recover so by subtracting n from it. So 6 minus 4, we know, oh, the original value is 2. And we'll go to index 2, which is here. And we add n to it. So 4 plus 4 is 8. Okay, good. Now we'll move to next number, which is 8. And then 8 is larger than n. And the original number is therefore 8 minus 4, which is 4. And you go to index 4, which is here. You add a 4 to it. 7. Good. And then you move on and you go to here 2 again. Now, if you go to index 2, you see that number is larger than, and then you realize, okay, well, I've encountered this number 2 before. So that's the duplicate you are looking for. Okay, so what we can do is n is equal to random number minus 1, and for 8 num in enumerate. Okay, enumerate from left to right. First, if the number is larger than n, we know it has been modified before, so we subtract n from it to recover the original value. Then you go to the destination and check if array at num is larger than n. If so, we know the number has been recovered, has been visited before. Otherwise, you just add n to it. And we're guaranteed that we're always going to find this duplicate within this iteration. So we should never get out of the iteration. If we ever do, then we should raise some type of exception. So let's test it out. Okay, we passed the local 2 test and just submit it. Good, there you go. We passed all the tests and we have a O(n) time complexity algorithm and an O(1) space complexity. And one last question, is O(n) the best thing we can do? Yes, because think about this way, you have to visit every element at least once to be able to find the duplicate. So O(n) is the lower bound, therefore O(n) is the best time complexity. However, if the input array is sorted, then I think we can do better in our log n, because if the input is sorted, and then we know everything is between 1 and n, so it would be something like 1, 2, 3, 4, 5, 5, 6, 7, 8. So we can probably do a binary search where we'll look at the middle. If the middle is exactly the middle number between 1 and n, then we know it's not in the first half, because if the duplicate is in the first half, we'll, in a sense, you will use one more space. So the number in the middle will be one less than the actual number should be in the middle. And then yeah, that's how you can divide the space by 2. We can quickly run like an example here. Imagine the input is sorted. Now, this is slightly problem, so like a follow-up question. So assume input is sorted, and then we have an array like 1, 2, 2, 3, 4. And of course, we can always scan from left to right and then found the JSON number that is equal to itself, but that will be an O(n) solution. Now we're concerned about, can we find a log(n) solution? So in this case, the total number is 4 from 1 to 4. And if we look at the number in the middle, which is index 0, index 1, index 2, index 3, index 4. So if we look at the index in the middle 2, well, what do we know about it? We know that it should, if the duplicate is in the middle, sorry, if there's no duplicate in the first half, then they should be something like 1, 2, 3, all the way to the middle point. And then what we should observe if there's no duplicates in the first half is something like, so the mid is equal to low plus 2. And the number in the mid should be equal to mid plus 1. So in this case, 0 plus 4 divided by 2 is 2. And the number should be 3 if the duplicate is not in the first half. In other words, it will be in the second half. Otherwise, if the number in the middle, as in this case, is not equal to mid plus 1, in fact, it will always be mid, then we know the duplicate is in first half. Yeah, I think then this is how we can, in a way, binary search the input and find out where the duplicate is. Yeah, that would be, I will leave out the details for you to think about how do you actually implement this, but that can be the general strategy. Thank you.